Welcome to solverfy.
Chapter 27, problem number 36 from the Smith Organic Chemistry textbook. And in this problem, we're given a molecule P, and we're asked to form it, or we're told that it can be formed either by thermal electrocyclic ring closure or photochemical electrocyclic ring closure. And we're asked to draw the two starting materials, the one material for each possible pathway, and to talk a little bit about the stereochemistry. And so we'll start with the thermal electrocyclic ring closure from unknown molecule Q. And so we're basically, we know that we need a system that's going to close down to form this four-membered ring and the eight-membered ring to which it's fused. And so we will start like this with this structure. It looks almost like two six-membered rings sort of stuck together. That doesn't look great. I'm going to redraw some of that. Right. So basically like two six-membered rings that have been stuck together, but it's not truly fused. This bond here, if that was there, that would be two fused six-membered rings. But we don't have a bond there. And so we know that there is one double bond in P, the product, the molecule that we were given. And so since there's one double bond in P, and we're doing an electrocyclic ring closure, we should know that there will be two double bonds in each Q and R. And so we have this backbone that'll close down to form an eight-membered ring fused to a four-membered ring. And we pretty much just need to place where the double bonds are. And so we know that a thermal electrocyclic ring closure from a two double bond molecule is going to be conrotatory. And so in order to get the stereochemistry that we need in the product, which is this cis stereochemistry, these two hydrogens are both on wedged bonds. In order to get that stereochemistry, we need to place these two double bonds in conjugation. And since it's going to be conrotatory, and we can actually go ahead and write that in here, it's going to be conrotatory. And since we know that, we should know by this point in the chapter that we're going to have opposite stereochemistry on these two double bonds. And the only way to really do that in this backbone molecule that we've drawn is to put one there, and that'll be the Z, the cis double bond. And then we'll put one here, and that will be a trans or an E double bond. And so when this ring closes down with a thermal electrocyclic ring closure, these bonds are going to do conrotatory rotation, and they'll end up putting the hydrogens in the same plane. And so, of course, looking at molecule R, the backbone is going to be exactly the same. So we can go ahead and draw that same backbone that we used for molecule Q. So there's the backbone. And then, of course, so again, we're starting from two double bonds. We're doing an electrocyclic ring closure, but this time it's photochemical instead of thermal. And so we should know by now that this will be a disrotatory electrocyclic ring closure. Disrotatory. rotatory. Yep. Okay. And so since this is going to be disrotatory, and we need this same stereochemistry on these two hydrogens, we have to make both of these double bonds either Z or E, but they do both have to be the same. So because this is a 10-membered ring that we've drawn, it's not big enough to contain two E double bonds, so they should both be Z double bonds. And again, they are going to have to be in conjugation so that this paracyclic reaction can take place. And so the only way to really fulfill those qualifications is to put them both there. And so they're both Z, both cis double bonds, and yeah, and so when treated with some light, that will do an electrocyclic ring closure, and the resulting stereochemistry will be the stereochemistry that we're looking for here in P, because it will be a disrotatory reaction. And so that is the answer to chapter 27, problem number 36.